tricky in general with that base classifier is that the reasoning that you have to do to establish it is not completely straightforward. It requires a little bit of intellectual gymnastics to actually go over it and understand what's going on. So I'm going to try to go as slowly as possible. Let me pull up my slides here. So let's establish that little result proof. So the first thing that we're going to do is we're going to try to think about the classifier less in terms of what it does, but in terms of the decision regions that are associated to it. Okay, so we're going to fix the classifier H. Remember, we're trying to find the best classifier. So here H denotes a generic classifier. And so for every label K, and my label K takes integer values by assumption between 0 and K minus 1. Just in terms of notation, keep in mind that that weird notation I'm using, where I'm using these intervals here with double bar, this is just a way for me to indicate that I'm looking at the sequence of integers. Now for a given H and for every label, we can define a decision region associated to label K for the classifier H. And that decision region, I'm going to give it a name. I'm going to call it capital gamma subscript K of H. Okay, so it is the decision region for label K of the classifier H, and formally, by definition, this is equal to the set of points, so the set of feature vectors X, if you wish, that take value in X, that are going to be classified as label K by your classifier. Okay? So the intuition that you want to have here is that I'm doing the following. I'm imagining that if I'm given a classifier H, and if I look at this big potato here as the set of all possible feature vectors, what I'm saying here is I'm saying that that set of feature vectors can be partitioned into a set here where every subregion corresponds to a decision region where your classifier assigns one and one only label. So for instance, here you would assign label 1, here label 2, label 3, label 4, label 5. So just be careful with that little illustration here. I'm not claiming that this is representative of what really happens, in the sense that there is no reason for the regions to be connected. It could be that you assign label 1 to points that are actually in regions not connected to each other, but I'm just illustrating the fact that it's a partition. And the one thing that I hope you're convinced of is that whether I talk about H in terms of a function, or whether I think about H in terms of the partition of decision region that it introduces, is completely equivalent. So when I'm talking about finding the H that minimizes my true risk, I can equivalently think about finding the partition of decision regions that minimizes the risk. So it might seem like a complicated and convoluted way to go about it, but as we'll see, this is what will allow us to actually go to the answer. So now what we're going to do is we're going to rewrite the risk explicitly. Okay? So what we're going to do is we're going to say the following. Let's look at 1 minus the risk. The reason I write 1 minus the risk is that in the context of the assumption that we've made, 1 minus the risk is merely the probability that the label that you assign to an unseen example X is equal to the correct label, Y. The risk is the probability that you make a wrong assignment. 1 minus the risk is the probability that you make a correct assignment. And what we're going to do, we're going to express that quantity in terms of the decision regions. The way I'm going to go about it is as follows. The first thing I'm going to do is I'm going to expand this term here using the law of total probability. Specifically, I'm going to write it as a sum from k equals 0 to k minus 1, probability that y is equal to k times the probability that h of x is equal to k given y is equal to k. I'm just using the law of total probability. Now, if you remember correctly, this p of y equal k, this is what I call pi k, according to my terminology. This is the a priori probability of your label. And then probability that h of x is equal to k given y equal k, I didn't give a specific name. Eta k is probability of y given x, here is probability of x given y, so I have to be a little bit careful. But I can express what that is. Indeed, if I expand again, I can write that as the sum from k equals 0 to k minus 1 of pi k. Now, what is the probability that h of x is equal to k given y equal k? I don't know, but I can express that as the integral over the decision region gamma k of h of the distribution p x given y of x given k dx. All right, so what I'm using here is the definition of what p of h of x equal k given y equal k. You know that you're going to get h of x of x equal k if given y, you generate an example x or a feature vector x that falls in the decision region where you assign a label k. And this is exactly the definition. All right, so now I'm going to call that expression star. If you want to minimize the risk, you should maximize 1 minus the risk, which means that you should maximize the expression that I'm indicating here. Okay, so to minimize the risk, we should maximize the expression star. And to understand how we can actually solve that maximization problem, let's think a little bit about what's happening here. So remember, what's a bit challenging here in that formalism is that what we're after the best classifier, or equivalently, we're after the best decision regions. So the unknown quantity that we're trying to optimize is actually gamma k of h, and more specifically, the set of gamma k of h. So let's think about it in the context of the equation star. What is the choice of gamma k of h that would guarantee that you get the maximum value of that equation star? Well, what I'm claiming is the following. I'm going to say that the optimal choice is to choose gamma k of h as follows. It's going to be the set of points x in x, remember it has to be a subset of the set of all possible future vectors, such that for every L that belongs to 0k minus 1, so for any label L, it holds that if you compute the product of pi L, my a priori probability of label L, times p of x given y of x given L, it is less than or equal to pi k times p of x given y of x given k. So why is it, as I claim, the optimal choice that you can make here? Well, that's the optimal choice because if you were to make any other definition for the decision region gamma, you would only reduce the value of the risk. And it's good to think about it in terms of buckets here. And I'm going to illustrate that here, even though once you get the explanation, you'll see exactly why I was going that fast about this explanation here. Let's look at the expression star here, and let's look at it just in the context of two labels. So I'm going to assume only that k is equal to 2 here, in which case star takes a very simple form. Star is going to be of the following form. It's going to be pi 0 times, oh sorry, let me rewrite it just slightly differently. It's going to be the integral over gamma 0 of h of pi 0 times p of x given y of x given 0 dx plus the integral over gamma 1 of h pi 1 p x given y x given 1 dx. I'm going to make one more simplification here to make my illustration even easier. I'm going to assume that my distributions are actually discrete and not continuous, as I suggest here, which really means that I can replace my integrals by sum. I can get rid of the differential elements and make everything look a lot easier. So what's happening here is we're saying the following. We're saying that we have a set here, capital X, that we partition into two regions. There's one region here that we call gamma 0 of H, and one region that we call gamma 1 of H. Now, once you fix the region, we're saying that every region contributes to the risk by bringing a cost associated to a specific point, which is given by this quantity here, which I call 0, if you belong to region 0, and given by that quantity there, if you are in region 1. So the cost of making a decision is related to the decision region that we're defining here. And so you see that if you want to minimize the cost, the idea is that you want to take any given point, which I'm going to include in red here, should be put in the region for which the cost is minimal. So for instance, for that point in red here, this point here corresponds to a situation where I can guarantee that Pxy, Pxy, x given 1 is larger than Π0, Px given y, x given 0. And therefore, I decide that that point should be in gamma 1. Okay, and so you can do that reasoning for every point in the space X, and it leads to the conclusion, which is almost by definition, that the optimal choice of gamma k of H is the one that I'm giving you over there. Okay, so you're effectively saying that you're choosing gamma k of H to be, by definition, the region where the cost associated to making a decision when you've decided that you fix the region gamma k of H as such is minimal. So I hope that explanation is clear. It's always boggled my mind when I was a student, when I first saw these reasonings, but after a while, especially if you illustrate it with a little doodling, I think it makes a lot of sense. So with that said, it gives us exactly the Bayes classifier that we were after. Now, strictly speaking, you could argue that I have the Bayes classifier is actually not exactly of that form. If you go back to the theorem, it's presented in a slightly different form. And to convince yourself that the expression that we obtain is exactly the same, there is just one little manipulation to do that we're going to be doing together. So just as a note, when you make the comparison here, pi L Pxy x given L less than or equal to pi k x given y x given k, let me give a name to that expression. I'm going to call that expression dagger. Okay, let's maybe call dagger here. And so what I'm claiming is I'm claiming that the expression dagger is actually equivalent here to the following. It's the same thing as comparing p y given x of L given x times px of x, whether it's less than or equal to py given x of k given x px of x. So upon inspection, you will realize that px is the same on both ends, so you can simplify, and therefore that test that I'm making only amounts to comparing the conditional distribution py given x. And this is what I call eta k. So the test that I'm making here is essentially comparing eta L of x to eta k of x. So really, when I talk about my region as the one for which pi k px y x given y of x given k is the largest, it's completely equivalent to me saying I'm choosing the region gamma k of H to contain all the points for which eta k of x is maximized over all possible values of k. And that's indeed the expression of the Bayes classifier that I indicated earlier. So the second thing that we are proving in that lemma here is also an expression for the Bayes risk. Now that we have the Bayes classifier, it's not too hard to compute the Bayes risk by itself, but there's again some technicality which is associated to us being comfortable with manipulating probabilities. So just this once, I will go over that with you to make sure that we are indeed on the same page. So let's go again. Here specifically, I'm going to make the proof of the Bayes, the expression of the Bayes risk. So now we have the expression of the Bayes classifier. Okay, so recall, I'm going to rewrite it here for reference. So recall that what I called the base classifier, HP of X, is, as according to what we have proved before, the value of the label, the argmax over K of eta K of X. And I'm becoming a little bit lazy. I'm not reminding you what is the range of this lowercase k, but it's the range of 0 to k minus 1, all possible labels they can associate to my feature vector. Now, what is the base risk? Well, by definition, if you look at the base risk, it is, according to or the expected value over x and y of what? Of my loss function, which is the indicator function, h of x not equal to 1. So here, conveniently, I can manipulate that a little bit. I'm claiming that we can write that as 1 minus the expected value over xy of the indicator function of h of x equal to 1. What I have used here is that the indicator function of h of x equal to y is merely 1 minus the indicator function of h of x not equal to y, and I use the linearity of expectation. Now, we can now plug in, and if I'm a bit more specific, I should indicate that the classifier we're looking at is the base classifier. Since we have the definition of the base classifier, we can write that as 1 minus the expected value over xy of what? Well, indicator function. When is the result of the base classifier equal to y? Well, it's the case when the argmax over all possible labels that I assign of eta k of x, that's what my base classifier does, is indeed equal to 1. So what I'm claiming here, maybe a bit fast, is that this is actually indeed equal to 1 minus the expected value over x of the max value over k of eta k of x. Now I'm going a little bit fast here. With a little bit of practice, you can see that it's actually true, but I understand that everyone might be a little bit rusty with probability, so whenever you see something that is a potential source of confusion or is not clear to you, it's always good to go back to definitions. With probabilities, that's always what I would want to do. And so let's try to justify a little more how we can go from the expression on the second line to the expression on this third line. So I'm going to manipulate the term expected value of xy of the indicator function. So indicator function of the argmax over k of eta k of x equal to k. So what I'm going to do is I'm going to do the following. I'm going to rewrite my expectation over xy as first an expectation over x, and then there is an expected value over y given x, which I'm going to write explicitly as the sum over y, py given x, py given x, which is still a random variable here, int of what of my indicator function, argmax over all k, eta k of x, which is still a random variable, equal to my label, which is equal to y here. Now, if you look at this expression in the I, let's think a little bit. When is a term in my summation non-zero? Well, it's only non-zero if my indicator function is non-zero. My indicator function is only equal to 1 if the label y that I'm using is indeed equal to that argmax. And therefore, that complicated sum takes a much simpler form, because in that sum, there's actually only one point where it's non-zero, and that's the point where y is equal to the argmax. So it allows me to write that sum that collapses to one point as the expected value over x of the probability of x given y, with y equal to the argmax over k of eta k of x, given that you're evaluating at the feature vector x. But if you think about the definition of the argmax, py given x is exactly eta k given x. And so when I evaluate py given x at the argmax, the value that it outputs is indeed the max value of eta k of x. So we get the expected value over x of the max over k of py given x. And this is exactly what I call here eta k. And so the result follows. So again, there is not much super deep conceptually here. It's just a matter of being able to manipulate these quantities. And I can't insist more. It's important that you know how to manipulate expected values of indicator functions, because with training, you will be able to do these calculations much more naturally, and they do show up a lot whenever you do applied probability theory. So that's it. That's the base classifier. That's the best classifier than we can hope to design ever in a multi-class classification problem. But of course, it requires us to know Px, Py given x. Actually, if you look at it in the eyes, the only thing we really need is Py given x, the eta k, because this eta k shows up in the definition of the base classifier.